All right, so the purpose of the lab that we're going to be doing tomorrow is that we want to investigate and find out what are the signs that a reaction has occurred. How do we know that in a chemical reaction, the starting reactants are chemically different than the products of that reaction? Okay, so because we are at least somewhat certain that that statement is true, okay, that in a chemical reaction, the reactants and the products are chemically different, okay, there's got to be some signs that a reaction has occurred, right? Now, we're generally familiar with those signs. What are some of the signs that a reaction has occurred? Okay, we could have an energy change, either hotter or colder in some cases, exothermic or endothermic. Okay, what else? Okay, it could give off a gas. What else? Could have bubbles, which is usually the sign that a gas has been evolved, but not always. There could be a color change. Sometimes we get a precipitate because one of our products isn't soluble when both of our reactants were. Okay, so these are all the signs that a chemical reaction has occurred because they show us that what we got at the end of a reaction is different than what we started with. Okay? Like it's possible to pour two clear, odorless solutions together and suddenly have a really strong odor get produced. Okay? When the two things I started with had no smell at all. Right? That's a sign that I have something that I didn't have, at least initially. Something was formed that was different. Okay? Or I take two clear solutions, I put them together, and I get like a bright yellow precipitate. Okay? Well, I started out with two things that were soluble, and now I have something that's not soluble. So these are things that tell me what I have at the end is different than what I started with. Okay? The elements are all the same, but how they're paired up is different. Everyone kind of follow there? Right, so that goes back to Dalton's atomic theory, okay, where he said that in a chemical reaction, atoms can be separated, joined, or rearranged. Okay, we're essentially investigating that a little bit and trying to find out what are the signs that that has happened. That's the problem that we're investigating here. What do you have to do with the problem in your lab report? You have to put it in your own words as a question. Okay. So you have to restate what I have there in the form of a question. Obviously, on your lab report template, it just says problem and it's blank. You got to put something in there. Okay, our variables. Okay, for our variables, okay, we have to identify and explain our manipulated, responding, and controlled variables. Okay, so here's how this experiment is going to work. You're going to get a bunch of different materials, okay, and you'll know what they are this time. They're not going to be unidentified. Okay, you're going to mix together specified pairs of things. So you're going to take like substance A and mix it with substance D and see what happens, and you're going to whatever else. You're going to be a bunch of pairs that you're going to have to test and see what happens. Everyone kind of follow there, right? So every time we do this, we're testing a different pair of reactants. Every time we do this, we're testing a different pair of reactants. That was my subtle hint at something. Okay. Every time I test a new set of reactants, I'm hoping that I will get different. It's okay. Can you turn that off so I can concentrate? I'm still recording. Okay. All right. So every time I mix together a new set of reactants, okay, then I should see, hopefully, different signs of a reaction, or at least signs of a reaction, I'm hoping. Now, there are some things out there that affect how reactions occur, how quickly they occur, whether they occur, okay, things like that. So there are probably some things that I should control or keep the same every time I mix a different pair of reactants. Okay, I want you to think about what kind of things you should control every time you run a new set of reactants. Okay, some of them are things you're not really controlling. Okay, like for example, the temperature in the lab. Might stay the same throughout the entire procedure, and that might be important. Okay. Things like, how much of the stuff you put together could also be important. I'll let you come up with one more. I gave you two. Remember, we don't want to just identify our variables. We have to explain each one. Okay, so this is the manipulated variable because, this is the responding variable because, these are this is a controlled variable because, controlled variable because, controlled variable because we're listing how many controlled variables? 3. Okay, so keep that in mind. Okay, for our hypothesis, what 3 words go in a hypothesis? If, and then. All right, so I'm going to give you a little help here. I'm going to tell you what should go in each part. You have to kind of put the final thing together. Okay, so the hypothesis has to talk about how we can deduce that a chemical reaction has occurred when 2 things are mixed, because that's kind of the problem we're investigating. All right, so in the if part, you should probably tell me what happens in a reaction. We just talked about that. It was part of Dalton's atomic theory. Okay, so the if part needs to talk about what happens in a reaction. The and part describes the experiment. Basically, several different pairs of reactants are going to be mixed and observed for signs of a reaction. I mean, that's our experiment. You need to put that in your own words somehow, but that's describing the experiment briefly. Okay. So in the if part, we're saying what happens in a reaction. Then we're describing the experiment. What should I talk about in the then part?
What you think is going to happen?
Yeah. How am I going to know that a reaction has occurred? That's what should be in the then part. Okay. Probably talk about the signs of a reaction. What will be present? What observations are going to be made if a reaction occurs? Okay, so that lays it out pretty well for you. Okay, you just got to kind of put your own spin on that. Okay, so as I said, we're going to have several different pairs here that we're going to be investigating. Okay, pair 1, we're going to mix sodium hydroxide with ammonium chloride. All right, they're going to be 2 clear solutions. One might be slightly cloudy, but okay, for all intents and purposes, it's going to be 2 clear solutions. You're going to mix them together, okay, and then kind of record what happens. So what kinds of observations do we probably want to be watching for when we're mixing 2 things together and looking for the signs of a reaction? Temperature of them, all right? So everything's starting temperature will be the same temperature as the room, agreed? Okay, so when you walk into the chem lab, should you go find the thermometer and figure out what the room temperature is? Because that'll be the starting temperature for all of your reactions, right? What you'll want to do then, every time you do a reaction, is you need to have a thermometer in there. Okay, so when you put one reactant in, have the thermometer in there, and then put in the other reactant and record if any temperatures change. One thing you need to be aware of with those thermometers, try not to hold them with your, like covering up a lot of the thermometer with your fingers. If you do that, you will change the temperature of the thermometer and not the reaction. So there's a little glass loop at the top of all the thermometers. That's what you should hold them by. Okay, there's a tiny little glass loop at the top. If you hold by that, the temperature of your fingers will have very little effect on the temperature of the reaction. Okay, and then it'll make it easier to kind of record. Then we should be watching for the other things like color change, if there's a precipitate formed, if there's any change in odor or bubbling or any of those kind of things. Those are all observations that we want to watch for. Okay? And we're going to want to record if any of those happen in each pair. Everybody all right with that? Okay. One of the big things to come out of the first lab was that you didn't have big enough samples. Everything was done in that tiny little depression plate. It was hard to see everything and all that. So we fixed that. All of the samples that we're going to need are going to be on the front table in the lab. All right, it's going to look just like this. Each sample will have a couple of eyedroppers if it's a solution, or a couple of scoops if it's a solid, with the exception of zinc, which is this little metal stuff. You can pick that up with your bare hands. Okay, so if it doesn't have a scoop, just double check with me. Okay, but you can probably, if it's the zinc, you can pick it up with your bare hands. All right, the other stuff you need to be careful with, especially some of the solutions, because one of them's a strong acid, one of them's a strong base, some of them are not really good for you, contain lead, okay, things like that. So you want to be careful with those. The other thing you need to be careful of, if you forget which sample you took the eyedropper from, don't put it back. Eyedroppers are cheap, solutions are not. Okay, so if you can't remember, just say, Mr. Coder, I don't remember where I took this from. I won't even give you a hard time. Well, much of a hard time. Okay, I'll just replace when something looks like it's short. You chuck that eyedropper. Okay, I don't want the solutions contaminated because the reaction will then happen in my sample, and that's a little bit larger size than I want the reaction happening in for some of those. Everybody follow? Okay. So what we'll do is we're going to use what's called a watch glass. Okay, it looks like a really big contact lens, about this big. Okay, made out of glass. Okay, concave, so you can do the reaction inside this cup essentially. Right? It's transparent, which is good. Okay, because it'll allow you to see any color changes. But remember, you are doing this on the lab table, which is black. So if the color changes from clear to dark, it may not be as clear because you're doing that on a dark background. So I would suggest that on each one, you should probably put like a piece of paper underneath, okay, take it in and out just to make sure that you haven't missed a color change, okay, because the color was darker as opposed to lighter. Right? There's really only one reaction where that'll be important. Okay, all of the waste when we're done our lab goes in that waste bucket we used the last time. Okay, so in the fume hood, okay, rinse off the lab or the watch glass with the wash bottle, okay, and then take it back to your desk and rinse it with tap water and then dry it off. Always have it dried before you do the next reaction. Okay, everybody with me so far? All right, so we've talked about the problem, we've talked about the design, we've talked about the hypothesis, and now we kind of know what the procedure will be. Okay, we're going to be performing these pairs. Do you have to do them in order? Actually, you don't. It's probably better if we do this randomly, because otherwise everybody will be clamoring for the same sample at the same time. All right, so I would say, some of you can start off with pair 1, some of you start off with pair 7, somebody do pair 4 first. Okay, the only 2 pairs you have to do in order are pair 4 and pair 5. You have to do pair 5 after pair 4, because you're actually using the product of pair 4 as your reactant for 5. Okay, so that's the only one that actually has to be done in numerical order. The rest can be done in random order. All right, everybody with me there? Okay. All right, so we'll mix those pairs, and like I said, make sure you record your observations carefully. I mix everything uber strong. Okay, so all of the reactions have some definite sign that will be obvious that a reaction has occurred. Right? That could be that there's an incredibly obvious bright color change, okay, or an incredibly obvious precipitate formed, or that it's going to bubble and fizz and carry on, or it's going to stink to high heaven. Okay, one way or the other, there's going to be some very noticeable change. Okay, so just watch them all carefully. If you have any reaction and you're thinking my observations are nothing happened, then you might have done something wrong or you weren't being observant enough. Okay, but for every reaction, there's definitely going to be at least one of the signs of a chemical reaction occurring. Okay, for our analysis and interpretation, we're practicing kind of our writing reactions. So we'll start with predicting the reactions today, and then we'll look at what the proper reactions are later. What you'll have to write for each of the reactions is the reaction in words and in formula form. So I'm going to want to see each reaction written out in words Each reaction written out in formula form, balanced. Everybody follow? All right, so that's question number 1 in the analysis. Using words and formulae, okay, write the chemical equation for each reaction that occurred. Okay, except pairs 4 and 5, which we'll talk about because there's no way you can write those. All right. Then for number 2, okay, 2 of the reactions are going to produce precipitates. You will need to use your solubility chart to figure out what the precipitates are. Right? Everybody with me there? So once we've written out the reaction, all you have to do is look at the products and figure out which of the products wasn't soluble. There's your precipitate, okay, using your solubility chart. All right, conclusion, same as always, copy and paste your hypothesis, then explain why your data and analysis either accept the hypothesis or reject the hypothesis. And then sources of error, okay, come up with 2 things that you thought made the lab maybe difficult or that could have been better and suggest ways to improve them. So you got to find 2 things and think of ways to fix them. Questions on the expectations there? All right. Now, we're going to look at here, guys, is the reactions that are going to go on in this lab. Okay, what we want to do is predict the products of these reactions. Okay, so our first reaction, we've got sodium hydroxide, NaOH, reacting with ammonium chloride. What kind of compounds are those? What kind of compounds, guys? Ionic. All right, what kind of reaction starts with 2 ionic compounds? Double replacement. Okay, tricky one here. In this compound, which one of those is the metal? Okay, that stuff is ammonium chloride. Where would I find ammonium? In the polyatomic ions chart. If you look on your periodic table, and you'll need that out right now, okay? If you look on your periodic table, ammonium is in the table of polyatomic ions. It is the only one with a positive charge, which means it's the only one on your chart that behaves like a metal. Okay? Ammonium is a complex ion that behaves like a metal. Okay? So according to what we know about double replacement reactions, I should swap the metals. Okay? Which means that ammonium and sodium are going to switch partners with each other. Everybody all right with that? Okay. So when that happens then, that means that ammonium should end up with hydroxide and sodium should end up with chlorine. Okay, then I got to check my drops and swaps. Ammonium's a +1, hydroxide's a -1, so that's okay. Sodium's a +1, chlorine's a -1, so that one's okay. Right? And then it's also already balanced. Now, does that necessarily mean I've predicted that according to the rules we learned? Does that necessarily mean that's the way the reaction will go? It might not. Okay? What we have to do tomorrow in the lab is find out. Okay? And if it doesn't go the way we thought, then we have to re-examine, okay, what we predicted. Okay, in pair number 2, okay, I have CH3COOH reacting with sodium hydrogen carbonate. Now, again, we've got a lot of stuff from the table of polyatomic ions. You should be able to find this ion on your table of polyatomic ions. What's it called? Yep. Acetate. Okay, this stuff is acetate. Now, the odd thing about this is that this compound is not written the way it should be because CH3COO has a negative charge. Hydrogen has a positive charge and is acting as the metal. right? But because this thing here is organic, we write it differently. If we were writing it as a truly organic compound, it would be written like this. Okay, this would be our positive and that would be our negative. So we've got an ionic compound where hydrogen is acting as a metal, which means this stuff should be all ionic compounds where hydrogen acts as a metal are what? No. You would be right if you were going to say acids. Okay, this is an acid. Specifically, it's acetic acid, which is in vinegar. Okay, now the vinegar you buy in the store is like 95% water and 5% acetic acid. In the lab, it's kind of the other way. Like I say, I like to mix things strong. Okay, we have what's called glacial acetic acid, which means it's basically 100%. Okay, acetic acid. You drip that on the lab table and it'll eat a hole in it. It'll eat your food for you. If you like vinegar on your fries, if you put it on there, it would eat them for you. Okay, don't drink it. It smells like vinegar. Be the last thing you taste if you drink it. Okay, so don't drink it, even though it might smell good. Okay, so we're going to have vinegar, and then we're reacting it with sodium hydrogen carbonate. What's the more common name for that? You did this reaction in elementary school. What did you mix vinegar with? Baking soda. Okay, that's vinegar and baking soda, except lab grade. Okay, not grocery store grade, lab grade. Okay, so we have really strong acetic acid being mixed with baking soda. Okay, so we know what kind of happens in that reaction, but it should still be a double replacement reaction. So hydrogen and sodium are the metals. They should do what? They should switch places because it's a double replacement reaction. So that means Na will end up with acetate and hydrogen will end up with this other stuff. Okay, again, that's the way our rules have taught us we should predict it. But what happens when you mix vinegar and baking soda? What does it do? It blows up. Yeah, it bubbles and fizzes. What does it produce? Okay, it produces a gas. Are either one of those compounds a gas? They are not. Okay, so chances are we probably didn't predict that one right. That's okay. I'm not marking your predictions. Okay, I'm going to mark your actual reactions, and we'll talk more about those after we've done the lab. All right, so what I want you to do now is do the rest of these predictions. Okay, so fill in the rest of the predictions, and then did I put an observations chart in that lab for you already? I think I did, right? Okay. You'll need to make a paper copy of that for tomorrow to record your observations in, because obviously we don't take the Chromebooks into the lab. Okay, so either print that or just quickly draw a hand copy of it on loose leaf, okay, so that you have that. I'm going to give you until about, let's say, 2:45 to work on the rest of this pre-lab stuff. So get your variables, hypothesis, okay, these predictions. That stuff all needs to be done before we go to the lab tomorrow. So I'll give you till 2:45 to work on that, okay, and then we're going to go back into predicting the products of a reaction because we got to make sure we know how to do that. Okay, all right, have at her.